since we can for today. So this is 1/5/2015. That's so crazy. Okay, and this is page 133. This is just the picture for number 1. So what we have is a dog. When I said it's a rough picture, it's a rough picture. That's our dog.
Is that a pun?
That is,
Rough.
oh, no, but it could be, I suppose. Here, we'll put it looks more like a sheep, but oh well. Man is pulling on his dog with a force of 70 newtons directed at an angle of 30 degrees above the horizontal. So when we do our force diagram, whoops, there is the force on the dog. And we could say force of man on dog. And this is 70 newtons. And this angle, we'll do this. That theta is 30 degrees. Not 300 degrees, 30 degrees. Okay. So all it's asking you to do is to find the x and y components of the force. So this is actually more straightforward than a lot of the other ones. X component, force man on dog x, and this would be force of the man on the dog y. So how do you solve that? It's trig, yeah. That's all it is. That's just simple vector resolution. Yes, sir.
Can we write it as, do we write it as in like x, y, or do we write it in x equals y equals? Does it matter which way we write it?
What do you mean?
Like, parenthesis x comma y. See, is that how we do that? Like it wants to know where the x and y are, do we write it?
Yeah, it's just
We just put y equals
Okay.
this, x equals
Well, f on the x, f on the y.
Okay.
You have to specify that it's not x equals. That's a point. If you're saying x equals blah blah blah, you're talking about a point on the x-axis. We're talking about the force on the x-axis. So it's a vector oriented to the x-axis. Those are different things. Don't do that. So, f of x is equal to, and in this one, I do the force of the man on the dog on the x, force of the man on the dog on the y. Well, on this one, there's only one force. It's not that bad, but we will get into problems where you've got, 4 or 5 forces acting on an object. And so it's really useful to put in your little subscripts. We of course, use, force of gravity on the x, force of gravity on the y, force pulling, force of tension, force of Jack, force of Shannon, whatever. So as we get into more complicated problems. Okay, does that help on number 1?
Yeah.
Okay. Your little committee, which was basically Josh, selected number 2 to do together. And so we'll do 2 together. I'm not worried about you not having enough problems to do on this stuff because I'm going to give you a buttload of problems to do on this stuff. So here we say that there's a crate pulled to the right with a force of 82 newtons, to the left with a force of 115, upward with a force of 565, and downward with a force of 236. So first we got to draw the crate. And since we're talking about left and right and up and down, we're looking at this thing sideways on. And so I will color code my forces just to be as helpful as possible. And we're told it's got a force to the right. So we could say force to the right of 82.0 newtons. And we want to remember to try to make these things at least roughly proportional. So we want our line, whoops, not to do that. We want our line to the left to be bigger than our line to the right. So this would be force to the left of 115 newtons. And we'll pick something that will show up, hopefully. So we have a force up, and this is going to be impossible to do proportionally because let's see what I can do here. Force up of 565 newtons, and we have a force down of 236 newtons. That's your, whoa. Okay, so that's your free body diagram. And starting off with one of these for every single problem you do is essential, because that gives you your layout. So it wants you to find the net force on the x, the net force on the y, and then the total net force. So to do any of these, I'm going to shrink this whole thing down now that you've seen it. So if we're working with our net force, we'll start on the x. Force net on the x. Well, it's equal to force left plus force right. And we know that those are in opposition, so one of them is going to be a negative. You know, and honestly, actually, I suppose it's more common to make that one the negative. So let's stick with convention, shall we? There. Okay. So force right plus force left. And by convention, if we're looking at this on an x-axis, which one is positive?
Right.
The force right. That's the one that we traditionally call positive. Now, of course, the catch comes in that force left is larger. Here's the thing. It doesn't matter if you go with convention or not here. You can look at the two forces when you're dealing with one axis and say, left is bigger. Let's make that our positive. You know, so we can do it either way. And actually, let's go ahead and we'll do that, just to keep our brains simple. So force right, and of course this then we've assigned as a negative, negative 82.0 newtons plus 115 newtons. Okay, so the net force on the x is 33 newtons to the left. Because remember, this is a vector, so we have to include a direction. So, I mean, it's that easy to get your net force on the x and y. What do you need to do to get your, well, let's do the y, and then we'll talk about what you need to do to get your overall net force. So we have F net on the y, well, that's equal to F up plus F down. Okay, and we, again, traditionally we would say that the up is positive, the down is negative, and that works out well for us in this case because up is the larger, so 565 newtons, and that's up, plus a negative 263 newtons, that's down. The F net on the y is equal to, yeah, my dyslexia kicks up every now and then. Okay, so F net on the y is 329 newtons upward. Okay. Easy. For how many of you is that pretty simple? Okay. Now, how many of you can immediately visualize the next step, finding the overall net force? It's Pythagoras. Yeah, it's just Pythagoras here. So we'll shrink this. And just like when you were doing non-perpendicular vectors, you're going to create an overall force triangle. So you've got a crooked line. on this box, you have 33 newtons to the left. And this is not at all to scale. Box. There. 33 newtons left. Still not very well to scale. And 329 newtons up. So if we take our vectors and we rearrange them, this is important because remember the force has to be coming from the center of the object. So if we take that arrow and we move it over here so that it's head to tail, then we can do the following. We can make our resultant there. Because remember, for our resultant, we're going to need not only magnitude, but heading. Yeah, we're going to need a heading. So there's our Pythagoras force net is equal to the square root of force net y squared plus force net x squared. Okay, net force is equal to 329 newtons squared plus 33 newtons squared. Net force is equal to, okay, so we have a net force of 330.650873, etc. newtons. We won't sig fig that just, well, we can write our answer up here and we can sig fig it. We have, what, 3 sig figs? 331 newtons. At, we need a heading. So this is where we'll have to go back to trig. Shrink that. Gesundheit. So we're looking for that angle. And so tangent of theta would equal the opposite over the adjacent would equal 329 over 33. So theta would equal inverse tangent of 329 newtons over 33 newtons. That would pause itself. Okay, so we've got theta is equal to the inverse tangent of 329 over 33. 329 divided by 33. Second function, tangent of that. So we get theta of 84.27216.468 degrees. How do you describe that angle?
The left above.
Is there any north, south, east, or west in this?
Left above. Left above.
Let's see. Remember that we're looking at it from this. Well, I would say left and above the horizon. Left and upward. Because it's both to the left of the object and above the horizon. You know, I don't know how your book, what does your book use it? They do counterclockwise from the positive x-axis, and they do the 330 degree, 96 counterclockwise from the, that's awful. I like left of the object and above the horizon, yeah. You know, and again, we get into the same thing we did with the other vector stuff of describing those angles in a way that's logical and clear, not ridiculous and not non-descriptive. Doesn't refer to frames that aren't there. Okay, that's what we'll do together today. I would like you to look at the 4A worksheet. You are assigned all of the 4A worksheet. So 4A worksheet all. And remember the big thing that we talked about? I know this was like, 4 million years ago, 2 weeks. Last year. Yes, last year, when we last left our physics heroes last year. If we have an object that is on a surface and it is neither sinking down into the surface nor rising up into the air, the force up and the force down on it have to be what? Equal. So remember that when you're looking at the 4A worksheet. And basically, I'm going to give you the rest of the time to work on the 4A worksheet, while I float around, help you answer questions, etc. So, that's it.